Welcome to Module 1, Introduction to Blockchain. In this module, we will try to understand the essential functions and building blocks of blockchain platforms. To understand blockchain, let us think about a simple scenario. Suppose buyer A wants to pay for a book he or she bought from supplier B. If buyer A wants to pay supplier B using the blockchain, both of them should be part of the blockchain's peer-to-peer network. While all participants do not need to install the full node of a blockchain that contains all the data stored in linked blocks, both participants would need to have light digital client, such as digital wallets, to carry out the transaction. Digital wallets are like bank accounts that can hold cryptocurrencies, currencies of the blockchain world. Digital wallets are associated with public addresses and private keys. Public addresses could be published on the blockchain peer-to-peer network as well as on web-based platforms, and senders could use the public address to send cryptocurrencies. The private keys are used by the owners of the digital wallets to sign the transactions, just like we sign transactions on our mobile banking apps through our password. If digital keys are lost, a user could lose access to his accounts. Let us suppose for now that both buyer A and supplier B have digital wallets on the blockchain. When buyer A fills in the message, that is the transaction details, recipient, that is supplier B's public address and the amount in cryptocurrency, and signs the transaction is published to the peer-to-peer network. Many transactions on the peer-to-peer network are then combined and time-stamped before being cryptographically hashed and validated by the miners, such as miner C, to form what is called blocks. Once the new block is created, the miner publishes the block to the peer-to-peer network for validation using consensus rules. More often than not, a 51% consensus is required to confirm the new block and add it to the existing chain of blocks, also sometimes referred to as distributed ledger of blockchain. Once the transaction is validated and added to the block, supplier B's wallet reflects the cryptocurrency as received. Anyone knowing the public address of supplier B's wallet could verify the amount and public address of the sender using open source programs called block explorers. In the previous slide, we have talked about the essential functionalities of blockchain platforms. In the next few slides, we will try to understand the basic building blocks of the blockchain platform. The most important building block of a blockchain platform are blocks and blockchain databases. So what are blocks? And how are they arranged in blockchain databases? Blockchain data is stored at multiple nodes in the form of chained blocks of information. Sometimes this approach is named as a distributed ledger system. Each block contains a hash, that is fingerprint of the previous block, the fingerprint of the new block, and public details of transactions that are stored in the current block. Since blocks contain the hash of the previous block, if you want to change information on a previously validated block, you will have to change and revalidate all the blocks that were validated after the particular block. And validation will require consensus from at least 51% of participants. The other most important thing to understand with respect to blockchain platforms or systems is consensus algorithm. But before we jump into what consensus algorithm is, we need to understand one important aspect of a distributed system. Since blockchain works on a distributed ledger, that is distributed nodes of databases, reliability of blockchain protocols is very important. What we mean by reliability here is that most of the blocks should reflect the appropriate and the most current state of the blockchain database. A reliable distributed nodes of databases must be able to cope with failure of one or more of its components. A failed component may exhibit a type of behavior that is often overlooked, namely sending conflicting information to different parts of the system. The problem of coping with this type of failure is expressed as Byzantine fault tolerance. One of the most crucial parts of keeping distributed blockchain database sanitized is by the use of proof of work consensus algorithms. Proof of work algorithms require miners or validators to find a piece of data that requires significant computation. For example, in the case of Bitcoin, miners must find a nonce, a numeric solution to the SHA-256 algorithm that meets a network. It requires finding the largest blockchain on the network to acquire the hash of the last block, and then repeated computations to find the nonce, which when added to the data of the new block results in the valid hash of the new block. Sometimes, finding nonce may require running the SHA-256 algorithm quadrillion times. Once the nonce is found, the miner publishes it to the network along with the nonce. The other miners then could just use the nonce and the transaction data of the new block to verify its authenticity by running the SHA-256 algorithm only once. Imperative to note here is the fact that Bitcoin uses SHA-256 algorithm. However, other blockchain platforms may use different fingerprinting algorithms. One of the problems with proof of work algorithms is they are computation and energy intensive. Furthermore, proof of work computation intensity has given rise to mining pools that have centralized the mining power. Technically, if 51% of miners agree on subverting the blockchain systems can be hacked. For Bitcoin, the top 3 mining pools in China already control more than 51% of mining power. To overcome the centralization in mining, as well as reduce energy footprints for validation, the blockchain community is developing a proof of stake system. Proof of stake is a method by which a blockchain network aims to achieve distributed consensus. Proof of stake requires users to provide a certain amount of cryptocurrency as a stake to participate in the validation process. The proof of stake system allocates validation based on the amount of cryptocurrency staked by the validators. If the validator commits mistakes, he or she could lose part of his stake. Also, to get 51% validation power on the proof of stake system, validators would require control of 51% of cryptocurrency. For the current market cap of Ethereum blockchain, validators would need to control more than 13 billion worth of Ethereum to control 51% validation power. Furthermore, such a highly centralized system may dissuade users from joining the network as well, because one of the most important propositions of blockchain system is its distributed nature and its democratic consensus algorithms. Ethereum is developing a proof of stake system that is supposed to replace its current proof of work system. What happens if there is disagreement on the blockchain network? First, disagreements in the network on the blockchain protocol or state of blocks could lead to two different crypto platform creation. Such events are termed as hard forking. For example, Bitcoin was hard forked to create Bitcoin XT, Bitcoin Cash, and many other new cryptocurrencies that developed their protocol and transactions on the new platform. A hard fork could also be a result of significant change in the protocol on the blockchains, where almost all network members accept the protocol change. If all members agree to the major change and no one is willing to run old protocol and develop it further, a hard fork may result in the main crypto platform continuing without the creation of any new crypto platform. Blockchain, like other information system programs, requires updating of code and bug fixing for enhancing securities. So the code updating can be proposed by anyone and approved by the network participants. Most of the time, major forking is a result of protocol change. Sometimes, code changes may lead to support for new types of transactions and are compatible with old transaction types. In these cases, soft forking happens, where miners need to upgrade their nodes and software to support the mining of new types of transactions. Again, a 51% consensus is required to launch such changes. Such changes are termed as soft forking. Soft forking is always compatible with old mined blocks and data. Thus, in the case of soft forking, no alternative platform continues. A soft fork can also occur at times due to a temporary divergence in the blockchain when miners using non-upgraded nodes violate a new consensus rule their nodes don't know about. To sum up, now we have understood the basic functioning of blockchain. In explaining the basic functioning of a blockchain, we also named the building blocks, such as peer-to-peer networks, digital clients, messages, a consensus algorithm, consensus rules, and distributed ledger. In the following two slides, I have presented Ethereum blockchain as an example to understand different components of a blockchain. I will not explain the content of this slide in the video. Instead, the slide is available to course participants and they should try to understand it by themselves. You can use Google search or the book mentioned as the source on the slide to clarify your doubts. A soft copy of the book is available for free on the GitHub.